Hello and welcome to High Voltage Engineering. We'll be talking about generation of high voltages and currents. It's a module 2 rather, where we'll be talking about generation of high voltage AC, that is AC high voltages. Okay, so let us start. Now the topics we are going to cover in this generation of AC high voltages are, we'll be talking about cascade transformers, we'll be talking about resonant transformers, and we'll be talking about generation of high frequency AC high voltages. So these are the three topics we're going to cover. In the cascade transformers, we are going to cover the power supply for AC test circuits. So we have covered previously about generation of the DC high voltages. Now the AC high voltages, they basically can be done, the generation of AC high voltages is through the transformers. Okay, so we'll be talking about different kind of transformers here. Now we'll as an introduction of this generation of high AC voltages, we sometimes we think of that whether a bigger transformer is required for the generation of AC high voltages, but the using of bigger transformer has its disadvantages. So what are the disadvantages? So when the test voltage required less and about 300 kV, a single transformer can be used for test purposes. So only a single transformer can be used for test cases for less than 300 kVs. Now the impedance of the transformer should be generally less than 5% and must be capable of giving short circuit current for 1 minute or more depending on the design. In addition, the normal winding, namely the low and high voltage winding, a third winding known as the meter winding is provided to measure the output voltage. For a higher voltage requirement, a single unit construction becomes difficult and cost due to insulation problems. Moreover, transportation and erection of large transformer becomes difficult. These drawbacks are overcome by series connection or cascading of several identical units of transformers, wherein the high voltage windings of all units effectively comes in series. Now see we have seen the gist of this statements is that the testing for voltages lesser than 300 kV, that can be done by a single transformer. But if you require a bigger transformer, there are issues of insulations, and you need the more windings. Okay, and the impedance of the transformers will increase. Okay, generally it is 5% of the rating of the transformer. Now if the higher transformer is installed, the impedance offered by transformer will also increase. Moreover, the transportation, the erection of these large transformers are very difficult. So there are certain difficulties in creating a single huge transformer. Rather, what the solution of creating a high voltage AC is that we keep smaller transformers and keep them in cascade formation or in series formation. Okay, so we'll talk about cascade transformer here. On the right hand side, you see the schematic diagram of the cascade transformer. The cascade transformer unit, in which the first transformer is at ground potential along with its tank. So the first transformer is at ground potential, that is the transformer on the left hand side. Okay, the second transformer is kept on insulators and maintained at a potential V2, the output voltage of the first unit above the ground. So the second transformer is just the secondary voltage of the first transformer. The second transformer is maintained at that voltage. The high voltage winding of the first unit is connected to the tank of the second unit. Okay, so let's say the first transformer, the primary voltage is V1 and secondary voltage is V2. V2 is the higher voltage. Now the second transformer, which is connected to the input of connected to V2, is maintained at a potential of V2 above the ground. via insulations. Low voltage winding of this unit is supplied from the excitation winding of the first transformer, which is in series with the high voltage winding of the first transformer and its first high voltage end. So that is what we have talked. The rating of the excitation winding is almost identical to of that of the primary or low voltage winding. The high voltage connection from the first transformer and the excitation winding terminal are taken through a bushing to the second transformer. In a similar manner, the third transformer is kept on insulators above the ground of the potential of 2V2 and is supplied likewise from the second transformer. The number of stages in this type of arrangement are usually 2 or 4, but very often 3 stages are adopted to facilitate a 3-phase operation so that can be obtained between the lines. So what we have seen that one transformer gets connected to the other, and the third transformer is connected to the second transformer, and so on. So in this, like this, one transformer is cascaded to the other. So this is the way the transformer is cascaded, and the connection is done via bushings. What are bushings? Bushings are insulating paths where the wires move out of the transformer chamber. Okay, or otherwise the entire transformer this container or the metal casing that will get electrocuted. So in order that the wires get easily through the transformer casing, bushings are used. They are nothing but insulated channels, and through the bushing the high voltage part of the first transformer is connected to the low voltage part of the second transformer, and the high voltage of the second transformer is connected to the low voltage side of the third transformer, and so on. Now how many arrangement can be done? Normally get up to a maximum of 4, but you will get around 3 is which is seen, that is normal. Okay. Now we will talk about the supply and outputs of these cascade transformers. Supply to the units can be obtained from motor generators, so generator set, or through an induction regulator for variation of the output voltage. So the supply from the cascade transformer are motor generators set or an induction generator. Okay, the rating of the primary or a low voltage winding is usually 230 or 400 volt of small unit up to 100 kVA. For larger outputs, the rating of the low voltage windings may be 3.3 kV to 6.6 kV to even 11 kV. Okay, so these are the ratings and the outputs of the cascaded transformers. Now there is the previously which we have talked about the cascade transformer. It is a very normal and simpler scheme. Now there is a second scheme of cascade transformer that can be obtained. A second scheme of providing the excitation to the second and the third stages is shown on this figure on the right hand side. The isolating transformer IS1, IS2 and IS3. So please check the IS1, IS2 and IS3 on the diagram. Okay, so these are isolating transformers of the ratio 1:1. What are the isolating transformers? Isolating transformers are transformers which supply power from one end to the other without any electrical connection. Remember, the transformer supplies power from one end to the other using the electromagnetic induction, but there is no direct electrical connection between the primary and the secondary. So these transformers are there to isolate one unit of the other. There is no electrical connection between these units. Okay, so this isolating transformer IS1, IS2 and IS3 of the ratio 1:1 insulated to their respective tank potential and are meant for supplying the excitation for the second and the third stages of the tank potential. Power supply to the isolated transformer is also fed from the same AC input. This scheme is expensive and requires more space. The advantage of this scheme that we need to know is that the natural cooling is sufficient and the transformers are light and compact. Okay, the transportation of the assembly is easy. Also, the construction is identical for isolating transformer and high voltage cascade units. Three-phase connection in delta or star is possible for 3 units. Now, testing transformers of the rating up to 10 MVA in cascade connection to give high voltage up to 2.25 MV are available for both indoor and outdoor applications. So we need to understand, question may be asked that why the second scheme using the isolating transformers are used. So what are the advantages? One of the advantages is that disadvantage it is expensive and it requires more space, but the advantage is that there is more chance of natural cooling because there are more number of transformers, so cooling would be much more easier. Okay, and it will be light and compact. Okay, and even it is the transportation of this transformer from one point to the other, that is also easy. Now we'll talk about testing of high voltage apparatus using cascade transformers. Testing of a high voltage apparatus or insulation always involves supply of capacitive loads with a very low power dissipation. If C is the capacitance of the test object and V is the RMS value of the nominal output voltage of the transformer at an angular frequency of omega, then the nominal rating of the transformer in kVA will be kV square omega C, where K is more than 1, which is a factor to account for any extra capacitance in the test circuit, like that of the measuring capacitance divider, etc. So basically, when we do the testing of of any apparatus, the apparatus testing, the insulation testing, what we are doing is basically testing of the capacitance of the object. Okay, so the power of the obtained or received on the object or the apparatus is kV square omega C. Now K is the value is more than 1 depending on the type of apparatus from this K is obtained if any extra capacitance is there in the test circuit. K may have a value of 2 or more for very high voltage of more than 1 megavolt. So these, if more than 1 megavolt is used for the testing of any appliance, there can be some stray capacitances coming into picture, and these can have an effect on the total power that is being provided by the cascade transformer. Okay, the typical capacitance value of high capacitance test objects like power transformer cables are as follows. So these are the list of different elements or appliances that are tested using cascade transformers, and the typical value of the high capacitance are given here. Now we will talk about the charging currents of the cascade transformers. The charging current of the test apparatus may be of the range of 10 milliamperes to at 100 kV to a few milliamperes at a megavolt range. So the current is around 10 milliamperes for 100 kV and couple of milliamperes when you boost the voltage to around some mega voltage. As such, the transformer should have only a short circuit time rating 10 to 15 minutes for high power rating as compared to those of the nominal power rating. So when we are using this testing, the testing should not be more than 10 to 15 minutes, because this rating, the high voltage that is being provided here, that cannot be used for a long period of time. So it is only for a small period of time, that should be kept in mind. Now we'll talk about cascade transformers, which are used in large testing transformers. Large testing transformer rated for more than 1 megavolt ampere at 1 MV are nowadays designed for outdoor use only. So there are large sized cascade transformers which we are talking about here. The design of the type mentioned in the second scheme and ensures that the unit are enclosed by large size metal rings to prevent corona. and are terminated with the near spherical polycone electrodes. So we have to use, for the high voltage, you have to use special electrodes to minimize corona. Again, what is corona? Corona is an effect on the atmosphere by this high voltage, where the charge particles becomes activated, and there is some kind of hissing noise or some blue glow that is basically almost the disruption or or breakdown of the air around the high voltage apparatus. So in order to reduce that, your the electrode shape should be changed, and it is basic and the best shape of electrode would be a spherical. Modern test transformers are built with to withstand transients during the flashover of the test object. However, particular care need to be taken to see that steady state voltage distribution within the cascade transfer unit is uniform. Okay, so you have to take care that the steady state voltage distribution throughout the cascade unit should be uniform. Sometimes reactor compensation may have to be provided for excessive load currents of the of capacitive nature. Now, whenever there is a apparatus to be tested which has a high capacitance, capacitive currents are drawn from this cascade transformer. With a smaller cascade transformer, that may not be very of a bigger concern, but for the high voltage bigger transformers, that may be a concern. So you have to add extra reactance or inductance to cancel out this capacitive current. So these are the compensator reactors. Okay, cascade transformers are very expensive apparatus and are difficult to repair. Therefore, it is necessary to limit the high short circuit current by using limiting reactor in the input stage. So why do we need a limiting reactor? In order to limit the high short circuit current. Now in the cascade transformer, we will be talking here about the power supply for the AC test circuit. Large cascade transformer units are supplied power through a separate motor generator set or by means of voltage regulators. Supply through a voltage regulator will be cheaper and will be more flexible in the sense that the unit in the cascade set can be operated in cascade or in parallel or three-phase unit. It is necessary that the impedance of the voltage regulating transformer is low in all voltage positions from minimum to the rated value. So in the power circuit, it is basically the cascade transformer is powered by separate motor generator set or by voltage regulators, where voltage regulator use is much more cheaper. Okay, and it is to be taken care that the impedance of the voltage regulating transformer is in the low voltage position. Now we'll be coming across another type. It's called the resonant transformer. Okay, so before that, we need to understand the equivalent circuit of high voltage testing transformer. On the on the left hand side, you have a transformer connected to a choke and the capacitance of the test object. Okay, now on the right hand side, the equivalent circuit is drawn, where you have the impedance of the primary and the secondary and the core losses being provided and shown in terms of a circuit. So the equivalent circuit of a high testing transformer consists of a leakage reactance of the windings, the winding resistances, the magnetizing reactance and the shunt capacitance across the output terminal due to the bushing of the high voltage terminal and also the test object. it may be seen that it is possible to have a series resonance at power frequency omega if L1 plus L2 is equal to 1 by omega c. So here we are talking about a resonance being taking place where the sum of the inductance of the two windings of the primary and secondary and the output capacitance of the apparatus are at a resonance at a particular frequency. With this condition, the current in the test object is very large and is limited only by the resistance of the circuit. So if you remember, if the resonance is occurred, the inductance and the capacitance cancels each other out, and you have only a resistance to resist the increase of the current, and hence the current will be very high. The waveform of the voltage across the test objects will be purely sinusoidal. Since it is only the resistance that is resisting the voltage and the current to the transformer, it will be purely sinusoidal, and there will be at a power factor of 1. The magnitude of the voltage across the capacitance of the test object will be given by this equation. So this is the Vc, or the voltage across the capacitor, can be given in terms of V by omega Cr, where R is the total series resistance of the circuit. Now in your previous semesters you have learned about the Q factor. So here the Q factor is also present. So the Q factor, we'll be talking about the Q factor and how the Q factor helps in this generation of high voltage, we'll see. So the factor Xc by R, that is 1 by omega Cr, is the Q factor of the circuit, and gives the magnitude of the voltage multiplication across the test object under resonant condition. So with the high Q factor, you will have high voltage across the apparatus in the resonant condition. Therefore, the input of voltage required for the excitation is reduced by a factor of 1 by Q, and the output kVA requires is also reduced by a factor 1 by Q. So what happens is that when we use a transformer here and we bring the frequency high so that it can experience a resonance, the voltage appearing across, since with a Q factor of high Q factor, the voltage appearing across the apparatus will be high. So we do not require that, we require a lesser voltage, so we can bring down the voltage and bring down the input. So from a smaller transformer with a different frequency, we can have a higher voltage. So this is the essence of this setup. This principle is utilized in testing a very high voltages and on occasion requiring a large current output, such as cable testing, dielectric loss measurement, partial discharge measurements, etc. A transformer with 50 to 100 kV voltage ratings and relatively large current rating is connected together with an additional choke if necessary. Now, why this additional choke is required? In order to minimize the short circuit current. The test condition is set such that the omega Le plus L equal to 1 by omega C. That is, Le is the total equivalent leakage inductance of the transformer, including the regulating transformer. Now we will see the advantages and disadvantages of Q factor. So the advantages of Q factor is given as it gives an output of pure sine wave. Since there is only resistance, so the output is purely sinusoidal and with a power factor of 1. The power requirement is less, so 5 to 10% of the total kVA can be used. No high power arcing or heavy current surges occur in the test object fails. So if the test object fails, there will be less amount of arcing and heavy current, as resonance ceases at the failure of the test objects. So how the high current is reduced? So when there is a failure in the apparatus, so the resonance, the circuit will be not in resonance, and the capacitance will be there, and hence the current will be reduced. Cascading is also possible for very high voltages. Simple and compact test arrangement, and no repeated flashovers occur in case of partial failure of the test object and insulation recovery. It can be shown that the supply source takes q number of cycles at least to charge the test specimen to a full voltage. Now we will talk about the disadvantages. The disadvantages are the requirements of additional variable chokes capable of withstanding the full test voltage and full current rating. So there are requirements of additional chokes. That is the only disadvantage with this system. Now we will talk about the series resonance test system. A voltage regulator of either the autotransformer type or induction regulator type is connected to the supply mains, and the secondary winding of the exciter transformer is connected across the HV reactor L and the capacitive load C. Okay, so you go and check the diagram on the right hand side. So we have a voltage regulator of which is either an autotransformer type or an induction regulator type, and it is connected to the supply mains, and the secondary winding of the exciter transformer is connected to across the HV reactor and the capacitor load C. So we have this regulator connected to an exciter transformer, which is connected to the reactor and the capacitor load. The inductance of the reactor L is varied by varying the air gap of the operating, and the operating range is set to the ratio of 10:1. The capacitance C comprises of the capacitance of the test object, the capacitance of the measuring voltage divider, the capacitance of the high voltage bushing. The Q factor is obtained in this circuit will be typically of the order of 50. Okay, so here how we are getting this resonance is that we are changing the value of the inductor or the reactor by changing the air gap. So once the resonance is formed, the Q factor can be adjusted to a range of 50. So essentially 50 times less amount of input will be required in order of testing. Now that was a series resonance system. Now it is also can be done in a parallel resonance system. So in the parallel resonance mode, the high voltage reactor is connected as an auto transformer and the circuit is connected as a parallel resonance circuit. The advantage of the parallel resonance circuit is that more stable output voltage can be obtained along with the high rate of rise of test voltage independent of the degree of tuning and Q factor. So this is the advantage that it is more stable output voltage you can get. The single resonant test system are built for the output voltage of 500 kV, while cascade units for the outputs of 3000 kV at 50 to 60 Hz. These kind of systems are available. Okay, so this is the end of this lecture. Thank you.